Hey everyone. So in this video, I like to say a few more things about solving trigonometric equations. So we've already solved a handful of trigonometric equations, but in all of our examples so far, we've really depended on our special right triangles. And so I like to cover a few examples where the special right triangles don't show up, or we'll have to use additional techniques to solve our equations. So let's start with this one here. We want to solve the equation sine of theta is equal to 2 over 3. Right, so sine of this angle theta is supposed to give us a y value on the unit circle, so here we can interpret this 2/3 as a y value. And we're trying to find all the angles possible that lead us to a y value of 2/3 is essentially what solving this equation is asking us to do. So here's a y value of 2/3. And it intersects, it crosses my unit circle at these two different points. So we get one family of angles. That would be solutions to this equation there, and we get another family of angles. That would be a solution to our equation there. So here maybe let me give these some names. Here maybe, we would, for solving these equations, we'll want to find one such example of an angle that lands at this position, and then we'll want to find all coterminal angles. And so let me say that theta 1 is the angle between 0 and 2 pi that brings us to this point, and theta 2, let's say it's the angle between 0 and 2 pi that leads us to that position there. If we could find theta 1 and theta 2 and list out all the coterminal angles, we'll have all of the solutions to this equation. And so maybe I'll just list this out. So solutions are, theta 1 plus 2 pi n, any coterminal angle with theta 1, and theta 2 plus 2 pi n. And so how can we find out what one of these angles might be? Well, this doesn't correspond to a special right triangle. It doesn't correspond to a 30, 60, 90 triangle. 2/3 is not a very familiar side length for our triangles. And so we can't really use that as a way of solving this trigonometric equation. But one thing we can do is we can use inverse trig. Right? So if sine takes an angle to a y coordinate on the unit circle, inverse sine does the reverse. It's going to take a y coordinate on the unit circle and it's going to bring us back to an angle. But it only gives us back angles between negative pi over 2 and pi over 2. So we have to be careful of that. Right, so here, maybe let's go ahead and write this down. So this really means that sine inverse of the side length, or we can think of it as the y coordinate, is going to give us back the angle. And it's a function, it's only going to give back one output. It's going to only give us one specific output for this input. Gives us back an angle between negative pi over 2 and pi over 2. Right, so it's going to give us back an angle in this interval here. And so sine inverse is going to tell us exactly this corresponding position, this angle, theta 1. Right, so here, if I compute sine inverse using just a calculator, it'll give us approximately 0.7297, and here I'm talking radians. And usually, if I don't include a unit here, we're talking about radians, but I'm just listing radians there just to be very, very clear. Okay, so that's this angle here, right? This angle, and so we have this family of solutions if we just add on 2 pi n. So theta, and I'll list the solutions out here. So theta is equal to 0.7297 plus 2 pi n. I guess I should use approximation. This is one family of solutions. And then, well, we still need to figure out the other family of solutions on the corresponding to theta 2, right? And if we think about this picture here, there is this triangle in this picture for theta 1. And really we can imagine that same triangle would have to fit on the other side of the unit circle as well. Right, so really, theta 1 also really belongs here in this picture. Right, it's this measurement there. That's the angle theta 1 as well. Those two triangles should be the same, and so that acute angle to the x-axis should also be theta 1. And so what this is really saying is that our other family of angles, maybe I'll use another color here. I've used green quite a bit. Let me use orange. So this other family of angles really corresponds to, well, it's kind of like going all the way across the unit circle to pi, and then taking away that angle theta 1. That's going to be the same angle theta 2, right? So here this is this other family of angles. Well, it's going to be pi take away our angle theta 1. Right, so it's going to be pi take away, here I can write it exactly as sine inverse of 2 over 3 if I really wanted to express this exactly. Maybe I won't put an approximation here. And you can notice that this would be the same value as 0.7297. So this comes out to be roughly 2.4119. So that's theta 2, and so the other family of solutions are coterminal angles to this angle here. And so here I'll write that out. So theta is approximately equal to 2.4119, right? So a little bit less than 3.1419, a little bit less than pi, is our other family of solutions. And so here I just want to point out that we had to depend a little bit on the symmetry of this circle, right? The fact that our first set of angles that we found from our inverse sine function, it's going to give us some angle, and we can kind of see this right triangle in the picture. And that to get the other angle, we had to see that right triangle kind of fit on the other side of the unit circle. And we had to really take away theta 1 away from 180 degrees or away from pi. Okay, so here, those are all the solutions to our equation sine of theta is equal to 2 over 3. So let's do this again, but now for the equation cosine of theta is equal to negative 3 over 5. So here, since we're dealing with a cosine function, we're saying that this angle is going to go through our cosine function, and it's going to give us this negative 3 over 5, and we can interpret this as an x-coordinate on the unit circle. Right, so if I draw my unit circle here, and we're saying negative 3 over 5 is the x-coordinate on the unit circle corresponding to these angles theta. Maybe 3 over 5 is there. So we're looking at any angles that bring us to this position, and any angles that bring us to this position. Right, but we just want one such angle, and then we can list out all the coterminal angles, and we'll have all our solutions. And so here, maybe let me list this as theta 1 is one solution from 0 to 2 pi here. And maybe I'll list out theta 2 as this angle here, between 0 and 2 pi. Okay, so here again, this isn't one of our special side lengths of a special right triangle, and so we can't really use many of the ideas we've covered earlier in the quarter, but we do have inverse trig to work with. Right, so here, if we're expecting cosine of theta to give us negative 3 over 5, then inverse cosine of negative 3 over 5, it's going to give us back one of these angles. It's going to give us back an angle. And just like sine inverse gave us back one angle, there's many different solutions to this equation, but sine inverse gave us back an angle between negative pi over 2 and pi over 2. Cosine inverse is only going to give us back an angle between 0 and pi. Right, so it's going to give us back an angle in this region here. So it's going to give us back, again, theta 1. And so when we compute this, when we evaluate this with a calculator, what we get is approximately 2.2143, again, radians. And so if I'm going to list my solutions, well, we get one such solution at this angle here. That's what we found at 2.2143 radians, and then any coterminal angle. So here I'm going to write this as theta is equal to, or maybe I should say approximately. So it's approximately 2.2143 plus 2 pi n. And so, right, I'm saying approximately here because this is some truncation of what we computed with the calculator. I cut off the end values of this long decimal, and so it's only approximately the right result. If we wanted the exact result, we could actually just write cosine inverse of -3/5. That would give us the exact value that should belong here, and then any coterminal angle with that, or in other words, plus 2 pi n on top of that, would be an exact solution to this equation. But again, that's not all of the solutions we want. When we were trying to solve an equation, we want to find all the solutions, and there's another solution out here. And actually, here I said theta 2 should be this angle, but it might be simpler if we actually let theta 2 be the negative angle. Right? Because cosine of an angle and cosine of the negative of that angle, they give the same result. And so I know that theta 2 here being the negative of theta 1 would give me that same -3/5 out as a result. And so here actually I know that theta 2, if I'm saying that it's the angle between negative, or between 0 and negative pi, would just be -2.2143. Right, this idea here is that cosine of negative theta, because it's an even function, it's the same as cosine of theta. And so I know that cosine of this angle and cosine of this angle are going to give us the same result. So this must be a solution if the original one, 2.2143 radians, was a solution too. So here maybe I can more concisely write this as theta is approximately plus or minus this angle plus 2 pi n. So sometimes solving trigonometric equations requires borrowing ideas from algebra. Right, so let's say I've got this equation here that I want to solve. 2 times cosine squared of theta plus cosine of theta is equal to 0. And so you might look at this and notice it looks a lot like a quadratic equation, right? 2x squared plus x is equal to 0. And how would we solve this equation on the right? Well, there's multiple ways of doing it, but I think the most natural way, or the quickest way, might be to factor. Right? They both have this common factor of x that I could factor out, and I have x times 2x plus 1 is equal to 0. And here we were multiplying two things and getting 0, so that's only going to be true, it's only going to work, it's only going to occur if the things we're multiplying are 0 themselves. So we get a solution when this left factor is 0, when x is equal to 0. We also get a solution when x is equal to, or not x, maybe I'll write 2x plus 1 is equal to 0. If that's 0, then of course it's going to multiply with whatever number x is and still be 0, and it's going to make the equation true. So here when we solve this equation, we subtract 1 from both sides, divide both sides by 2, and we get x is equal to -1/2. And here are the solutions to this equation in terms of x. Well, we can do exactly the same thing. All these ideas still hold for the equation we see there with cosine. And here, sometimes we can even view this as a quadratic equation in terms of cosine. And so here we can apply the same ideas. We can factor out that cosine of theta. Cosine of theta is just some number. And whatever that number is, I'm going to factor that same number out from both of these terms, and it's going to leave us with 2 times cosine of theta plus 1 is equal to 0. And we play the same game here saying, well, if we've got 2 quantities that multiply to 0, it's only going to be true when either one of these quantities is 0. So we get solutions when cosine of theta is equal to 0, and when 2 cosine of theta plus 1 is equal to 0. And so let me take this right equation a little bit further. When we subtract 1 from both sides, we get 2 cosine of theta is equal to negative 1. Dividing both sides by 2, we get cosine of theta is equal to negative 1/2. And now we have 2 friendlier equations that we still need to solve. And so here maybe I'll label these maybe equation 1 and equation 2 that we need to find all the solutions for. And so for equation 1, and we're looking at a unit circle, and we're asking, when are the x values, what angles give us an x value of 0? And so that's this horizontal line here. This is x is equal to 0. So we're asking what angles bring us to an x coordinate of 0 on the unit circle. Well, here, pi over 2. If I look on the other side of the unit circle, in other words, I add pi, I get myself to 3 pi over 2. I also get an x coordinate of 0. If I keep going another pi, I get myself to 5 pi over 2. And really the solutions to this first equation, I'll write my solutions out here. So solutions, theta is equal to pi over 2. That's one solution, and every time we cross the unit circle all the way to the other side, in other words, I add a multiple of pi, a whole number multiple of pi, onto pi over 2, I'm going to get another solution to my first equation, cosine of theta is equal to 0. But now we have to do the same thing, but with cosine of theta is equal to negative 1/2. Right, negative 1/2, well that's here on the unit circle, right? Here's an x coordinate, an x position of negative 1/2. And we can see that those occur at these 2 points. Any angles that bring us to these 2 points give us solutions to our second equation, which would lead to solutions to our original equation. And so here we get a solution when we go to, well, this would be at 2 pi over 3. This is a 30, 60, 90 triangle that fits underneath this angle here, with the 60-degree angle between the x-axis and our angle. And so what we're looking at here is that theta is equal to 2 pi over 3 plus 2 pi n, any coterminal angle with this angle here. But then we also have this angle below, and using our idea from earlier, really this would just be the same thing as a negative 2 pi over 3 plus 2 pi n, right? If I go in the clockwise direction, it takes me the same amount, 2 pi over 3, to arrive at the position on the bottom side of this x-axis. And so 2 pi over 3 in the clockwise direction, that's the same as negative 2 pi over 3. And so here if we have theta is equal to plus or minus 2 pi over 3, we get that top angle and that bottom angle, and then adding on our coterminal angles of 2 pi times n, that really captures all the solutions to this equation. Okay, so let's take a look at another example here. And we want to solve the equation 2 times sine squared of x minus 5 sine of x minus 3 is equal to 0. And much like our previous example, we see a quadratic equation in terms of a trigonometric function, this time sine, right? So this is a quadratic in sine of x. And because it's a quadratic equation, we can use our techniques from algebra, including factoring, completing the square, the quadratic formula. Let's try to see if factoring works here first. So here, if this is going to factor this left-hand side, well, I know I'm going to need a factor or a first term of 2 times sine of x and sine of x, so that these two would multiply and give me that 2 sine squared of x. And then so if I'm going to get this minus 3 out for my constant term, I'm going to need a plus 1 and a minus 3, or a plus 3 and a minus 1. But because this middle term is negative, I'm going to expect a larger negative result from multiplying these constant terms with our sine terms when I expand this back out. So I'm going to put a minus 3 here because I know minus 3 times 2 times sine of x, well, that would be a larger negative amount of sine of x. And then if I fit in a plus 1 here, then I would have plus 1 sine of x, and that would balance things out, right? If maybe just to really see that this is the true factorization, if we multiply this out, 2 times sine of x plus 1 times sine of x minus 3, well, we get that 2 sine squared of x. We get minus 6 sine of x plus 1 sine of x minus 3. And these two middle terms sum to that minus 5 sine of x that we were expecting. Okay, so we factored out this left-hand side, and now we get solutions whenever the factors themselves are 0. And so that happens when sine of x plus 1 is equal to 0, and when sine of x minus 3 is equal to 0. Let's start with the second equation. I can add 3 to both sides to get sine of x is equal to 3. And remember, sine of x is the y-coordinate on the unit circle, and because we're talking about the y-coordinate on the unit circle, that y-coordinate is not going to exceed -1 and 1. Right? The range of sine is between -1 and 1, and so here this contributes no solutions. Right? There are no solutions for this factor to be 0. And so there are no solutions being contributed from this factor, but we still might get solutions from the first solution, sine, or the first equation, 2 times sine of x plus 1 is equal to 0. So subtracting 1 from both sides, we get 2 times sine of x is equal to -1. And then dividing both sides by 2, we get sine of x is equal to -1/2. And so when we look at the unit circle, we're asking what angles give us a y-coordinate on the unit circle of -1/2. Well, right, that corresponds to any angle that brings us to this position on the unit circle and any angle that brings us to this position on the unit circle. And so here I can see that I get one such angle at I get one such angle at 7 pi over 6. Seven pi over 6, right? Sort of 30 degrees beyond pi, 30 degrees beyond 180. And then, right, that fits the 30, 60, 90 triangle into this picture with the short side length being the y-coordinate. And then we also get the coterminal angles would be solutions too, so plus 2 pi n. And then we get solutions at this angle out here, and that would be, well, you can read it as negative pi over 6 plus 2 pi n, or 11 pi over 6 plus 2 pi n, right? 30 degrees shy of the full rotation of our circle would bring us a 30, 60, 90 triangle in that position there, with the shortest side length being the y-coordinate in the negative direction. So sometimes we have to be a little bit careful with solving these trigonometric equations, and we want to be careful not to divide from both sides of our equation. Maybe I'll illustrate this with algebra first to see that this can lead to us missing some solutions. So if we want to solve the equation x squared is equal to 3x, right? To correctly solve this equation, or to really capture all of the solutions, right? Whenever we're trying to solve an equation, we want to find all the solutions. Again, there's many different ways to do this. I think factoring is the most direct. And so here we have x squared minus 3x. If we subtract 3x from both sides, we can factor that x out, and we get x times x minus 3 is equal to 0. And so we get a solution here. of x is equal to 0, right, when this first factor is 0, and x is equal to 3 when this second factor is 0. These are the two solutions. And here we can see a way to incorrectly solve this equation to miss some solutions. If we take that same equation and we divide both sides by x, right, I see a factor of x on both sides. What if I try to divide both sides by x? And then I end up with, well, x squared divided by x would give us x. And 3x divided by x would give us 3. And so we get the solution x is equal to 3. That's not an incorrect solution, but we're missing the solution of x is equal to 0. And so why are we missing the solution that x is equal to 0? Well, when we divide by a number to both sides of the equation, we're assuming that that number is not 0. Division by 0 is undefined, so we're just by trying to divide, we're already making an assumption that that number we're dividing is not 0. So here we're assuming x is not equal to 0 to perform this division. And so any solutions where that thing you're dividing is 0, well, those would not be found by this approach to trying to solve an equation, right? And so I guess what I want to say is that this isn't necessarily a wrong approach, but if you do apply any division in your approach to solving an equation, you want to be aware of when what you're dividing is 0, does that contribute any solutions, right? So if you were to divide x from both sides here, you just have to be aware that, okay, maybe x is equal to 0 is a solution to this equation, and I would have to check that. And so here, let's try and solve this equation here. Let's solve tangent of x times cosine of x is equal to cosine of x. And so here, I guess the point I want to make is, let's not divide both sides by cosine of x. They both have a factor of cosine of x, but if we divide out that cosine of x, we're going to miss any solutions corresponding to when cosine of x is equal to 0. Right, so here, what we want to do is we want to subtract away cosine of x from both sides. We get tangent of x times cosine of x minus cosine of x is equal to 0. And then we can factor that cosine of x out. And we get tangent of x minus 1 times cosine of x. That's equal to 0. And here we get solutions when cosine of x is equal to 0. And when tangent of x minus 1 is equal to 0. So we saw earlier that cosine of x is equal to 0 at these coordinates here on the unit circle, these points here at the unit circle. And so that occurs at pi over 2, 3 pi over 2, 5 pi over 2. And so here we can see that if I sort of list this equation as equation 1 and this one as equation 2, we have solutions whenever x is equal to pi over 2 plus pi times n. So those are solutions to our first factor being 0, and then solutions to our second factor being 0 occur when tangent of x is equal to 1, right? Adding 1 to both sides. And so solving this equation, maybe I'll clear up my unit circle a little bit. So solving this equation here, we're asking, when is the slope of our angle equal to 1? Well, that occurs at pi over 4. If we go around a full pi rotation, we get, or a half rotation around the circle, we get 5 pi over 4. And we can keep going and add on every pi and end up at that same angle, or at the same slope. And so really, the other solutions we get are x is equal to pi over 4 plus pi n. And so here I want to pay extra attention to the fact that here with the equation we started with, if we were to divide both sides by cosine, of x, well, what do we get here? We would get the equation tangent of x is equal to 1. And that corresponds to this equation here. But it would miss all of these solutions corresponding to when cosine of x is 0. And here it's clear that if we look at this equation, when cosine of x is 0, we are going to get a solution, right? Because whatever tangent of x is, well, that times the 0 from cosine of x and would still be equal to the 0 of cosine of x on the right side of this equation. So when cosine of x is 0, we get a solution, and dividing both sides by cosine of x would forget all of those solutions.